Hi everyone, I'm Liz, a first year PhD student in astronomy, and today is a special paper review because this is a paper review of my own first paper. It's a bit old. It's not that old, but it's like from the end of 2021. And the reason why I wanted to do this is that because this paper is in Russian, in an obscure local Russian journal, and this morning I just randomly remembered about it, and I thought, I don't really want it to go into obscurity. Because right now I'm pretty sure no one really has ever read it. It's on ADS, but again, due to it being in Russian, the accessibility of it is limited. I mean, you can always use translation, but services like DeepL or Google Translate. But no one's going to bother. I think. So it's kind of like a restoration project. I'm trying to save it from oblivion. This little paper of mine, it wasn't a great project. I didn't really like it, but it's still something I would like to. No, not restoration. It's preservation project. That's the right word. Yes. I wanted to preserve it a bit, despite of it. I'm also thinking of maybe I could translate it. It's not big at all, and publish it on archive. Obviously can't publish it in any other journal because this is the agreement that you make when you publish something in a peer-reviewed journal, that you don't publish it anywhere else. But an archive is fine. So at least this way, its results can be saved. And when I went through it to kind of to rehearse, I found that the result is actually quite important. Can be. So it's absolutely valid to try to do this preservation. And the story behind it, so this is a paper this is a project that I did in my third year of uni, and the thing is that on our major, starting from our third year, and we had a combined bachelor's plus master's degree, so we had all 6 years of study. Starting from third year, we had to defend mini theses each year, at least once. And when I say mini theses, I mean that the format, the the duration of your talk, the template for your report, everything is the same as for your thesis. In a way, it's just was the way to prepare us and to kind of familiarize us, so that at the point of a thesis, it's kind of mundane to us. It's nothing new. We're less worried. I think in retrospect, it's a good idea, even if someone might be annoyed by doing so many defenses. But yeah, and in idea, each time this mini defense is not supposed to be. No one expects from students to have a fully fledged, fully completed science project. No, it's not necessary. And in idea, I think that in the minds of people who have created it, it was supposed to be just regular reports on your progress for your one large research project that would you then compile and present as a whole as your thesis, right? Like, it's not that each year you come up with a full paper. Like, imagine if it would be like, like it's 6 people on average on one like year, and like 3rd, 4th, 5th year have this. So like it would be 18 people, each publishing a paper, each creating a paper worth research, and like the whole institute, just astronomers, creating 18 papers a year. That would be crazy. What a productive institution that would be, by all metrics. But no, that's not what happened. But anyway, and for my 3rd year, we did this little project that I did end up making into this sort of a test paper, like how to call it. It's not that serious, but at the same time, it is a fully completed work, I think. Okay, it's called, this long ass name, The Impact of Rates of Reactions with Cosmic Ray Induced Photons on Chemical Composition of Protoplanetary Disks. Okay, so protoplanetary disks again. I think maybe at some point it will be interesting to make reviews on. Oh no, I definitely will do, because actually, I don't really want to revisit this. But back in my uni, we had to do some actually paper reviews instead of exams. So I have material prepared to produce these reviews, but to be honest, they were kind of not low quality, but like, I cannot give the same depth as in case of protoplanetary disks, because this is my field, and I'm not that interested to revisit those. But now, as in my PhD studies, we also have some paper reviews as a form of exam, and I think that I will record in preparation. So there will be a few slightly off protoplanetary disk topic paper reviews in the future. But yeah. But anyway, again, protoplanetary disks, and now it's more chemically focused, and in protoplanetary disks, a lot of chemistry happens. And there is this type of reactions called cosmic ray induced reactions with cosmic ray induced photons. So what are those? So typically, if you take only stellar radiation field and interstellar radiation field, UV and X-rays can only go this far. So only like upper layers of the disk they can penetrate. But there are also cosmic rays, and cosmic rays can go very deep, almost to the midplane. And so these cosmic rays, they can hit molecular hydrogen, ionize it, most likely, and this electron that appears from this interaction with cosmic ray can then go on, hit other molecular hydrogen, maybe ionize, and maybe later on excite molecular hydrogen. And then this excited molecular hydrogen de-excites and produce photons. And as energy level transitions for molecular hydrogen is in UV, those photons are also UV photons. So cosmic rays in this way create UV photons inside the disk. like deep inside the disk. And this is the only source of UV photons deep inside the disk, which in turn interact with chemical species through photoreactions like photodissociation, photodesorption, maybe photoionization. And so, yes, so this is what are cosmic ray-induced photons, or we can call them CRIPs, C-R-I-P for short. And the reactions with them are just photoreactions with these UV photons. The rates of these CRIP reactions were calculated in 1989 by Gredel et al. And this is the formula that they have in their paper for producing these rates. Rates in the context of, rate equations that you solve to solve chemistry. And its idea is very simple. So zeta is cosmic ray ionization rate, so basically how frequent cosmic rays are. Then, so this is the rate for the chemical species M. This is the concentration of M, and then there is an integral basically averaging the interaction over the frequency. In the I forgot how it's called, but upper part of the division, you have the probability of this CRIP hitting exactly the chemical species M. So this is the cross section of interaction of CRIP with M, and this is the essentially its spectrum, but in a form of probability. So that's why it's kind of this. So actually, okay, never mind, a bit later. And in the, I think it's numerator and denominator, right? If I'm not wrong. And in the denominator you have a probability of a CRIP hitting anything else, any other species or dust. So very simple, like the reaction CRIP hits this molecule, the reaction CRIP hits anything else, divided by the probability of it hitting anything else. And initially, what our project wanted our projects to be is to just recalculate those rates and give them to the community. Because why actually? Because this result of Gredel was done for cold molecular clouds, right? We are in protoplanetary disks. Should the rates be different? Well, kinda. So on the one hand, here is of course all the abundances of molecules sit, because obviously if there is more of something, the chance to hit it rises. And this should be different, the cross section of dust, because it can grow. It grows in protoplanetary disks, and it grows to larger sizes than in molecular clouds. So in theory it should be different, because it should influence the denominator. And we wanted to recalculate it. But the biggest problem we've encountered is in getting this spectrum, because Gredel doesn't provide it, and they just have a plot in their paper, which is not really useful. And deriving it on your own is just quantum physics, and we both, with my supervisor, are not proficient in that, so it would take a bit too long that we would want it to be. So we decided to switch our problem. We decided to, okay. We can't recalculate. without too much effort. I know. We're just not specialists in quantum. That's it. Someone else should do it. I mean, it should be a lot. I mean, I laughed because I said that as if the research work shouldn't take effort. Of course it should, but it's just that it would require us to learn too much of a different field for that. Anyway, so what we decided to do instead is to just estimate how it would change in a protoplanetary disks due to the dust size changing, and see if it's important. Because if it's not important, we can just not recalculate and use the same ones that were calculated in 89 and not care about anything. So this is what we proceeded with. And what is the estimate that we made? So we did a few simple assumptions first. So first we assumed that the main drain of crypts is due to reactions with the dust. So most of the crypts get absorbed by the dust, not by molecular species, and therefore we can kind of cross this term out. And the second assumption is that this cross-section obviously depends on the wavelength, but we assumed that, and this I think this kind of backed up by actual plots of wavelength dependency of this cross-section, is that in this UV region that's relevant to us, it does not change that much, so we can just kind of forget about it, and we don't need to average it over the wavelength range. We can just take it as independent on the wavelength, and this creates a very simple proportionality, that the rate of interaction with the cosmic with a creep is inverse proportional to the cross-section of the dust. And for the cross-section of the dust, we decided to estimate just simply a geometric cross-section. So for a single grain of one size, it looks like this, but we have a distribution of grains of different sizes. We took the classic MRN one, and if you compute this averaged over the distribution cross-section, you get that it's inverse proportional to a geometric mean size. And I mean, by geometric mean size, I mean the square root of multiplication of minimum size of the dust to maximum size of the dust. Okay, so combining these two estimates, we get that this the creep reaction rate should be proportional to the geometric mean size of dust. Okay, great. And to investigate the impact on the chemistry of this change in the rate, we took Andes model, which is a astrochemical model of a protoplanetary disk. It's quasi-stationary, it's 2D axisymmetric. Quasi-stationary in the sense that chemistry is time-dependent, physics are not. Chemistry itself is just the rate equations, obviously, otherwise we wouldn't deal with rates. The network is from chemic model. This is the reference. Of course, obvious by now that MRN dust size distribution is used. from a size that is also classical to MRN up to an Amax, which we vary in our model. And I don't mention this in the paper, but I unearthed it. The parameters that we use for our disk is characteristic radius of 50 AU, the mass of 0.01 solar masses, and the star is 1 solar mass. And with these parameters we create 3 models. So the first model has the classic creep reactions. I think they're taken from KIDA, and in KIDA they are from Gradle, KIDA database. And also the dust, the maximum size of dust, just the same as in MRN distribution. In the second model, we increase maximum size by 100, therefore average size is increased by 10, but we keep reactions the same so that we can disentangle the effect of dust. And the third model, we just increase creep reactions by just manually multiplying them by the how they should increase and accordingly to our estimate, so by 10. And we explored 2 values, how they change between the models. So the first one that we looked at is the ionization fraction. So I think it's basically the ratio of concentration or density of all ions or all ionized species to the gas density or concentration, number density. Anyway, just a ratio of ionized density to gas density, essentially. And these plots are distributions of the differences. The first is this value evaluated for the second model divided by the first model, and on the right it's between third and second models. And we can see that the difference from the dust, for the change in the dust parameters, like increasing the dust size, is significant for ionization. There are 2 main things. So on the one hand, there is an increase in ionization fraction here in the upper layers of the disk atmosphere, and this can be explained just by dust becoming more transparent. So it kind of eats less of UV and X-ray and does not that can be used for ionization of other species. Although, no, I mean, it's not necessarily UV, because, you know, you can have different species. Because you can have different species and they have different ionization energies. So it's not necessarily UV, because, like, yeah. So, yeah, anyway, just the dust, because we decreased this, its cross-section is more transparent. You can see it by this AV isoline. This is AV 1.5. It fell down. Therefore, disk is more transparent, and the radiation can ionize more stuff. But here we see a decrease in ionization. That's because this close to the star, main ionization comes from dust, basically from dust being ionized, and because we decrease its cross section, it's ionized less, and therefore we see a fall here. When we compare third and second model, where there's only a difference in creep reactions, we don't see that much of a change. There is a little streak in this disk periphery, and this is where the iron fraction is dominated by C+, and C+ is does come from creep reactions. So creeps can ionize carbon, and increasing the rate increased carbon ionization here. In all other parts of the disk, the differences are negligible compared to what the dust does. The second thing that we looked at is the ice mass fraction. So basically, how much of the mass of the disk is contained in species frozen out on the ice. And this is a value that is integrated over the height. So this is why you have a radial distribution. And here we have all three this value for all three models. So comparing first and the second, what we see is the two effects. So first is that this distribution of the ice mass ratio, ice mass fraction, is shifted from the star. This is simply due to so whether something is frozen out on dust or not is determined by the balance between desorption rates and adsorption rates. And adsorption rates do scale with dust cross-section, because obviously to get onto the dust you need to encounter the dust. Desorption rates, on the other hand, do not scale with the dust size, because when you're on the dust you don't care how big it is, you care about the stuff like temperature. So adsorption decreased, desorption stayed the same. Therefore, at the same temperature, you get now desorption more dominating, so you need the lower temperatures to get onto the dust. And that's why you see a shift. This is the effect of dust. Here, this absence of this peak is due to disk being more, again, transparent to interstellar radiation, and therefore species get photodesorbed here more efficiently, because dust doesn't eat it. Although, you'd think, but again, to get photodesorbed, even if you're on an ice, it needs to kind of hit directly you and not just dust. So yeah, so it makes sense. But then when we compare the second and the third, this is the creep reaction rate increase effect, we see an order of magnitude dip in decrease in this value, in this region, from 2,3 AU to 30 AU. Concerning. There's also a small decrease, although in certain ways it can be around an order of magnitude as well. But yeah, we're also here. And if we look at who is the culprits, we see that, so for this region from 2 to 30 AU, at first the ice mass fraction is dominated by water, and then it becomes dominated by CO2. So the problem is in them too. So whatever happened to the ice mass fraction is hidden in whatever happened to them. And here, well, at this temperatures, this close to the star, obviously only complex organic molecules can stay on the dust, and something happened to them. Well, it's kind of obvious what happened to them, actually. I can tell you right away. They get photodissociated by Crips, and then these components that they have, broken into, they have a lower desorption temperature, and they just evaporate from the dust, and that's it. With H2O and CO2, there is a bit of a more interesting history, and for that we'll look at the concentration evolution at this location, at this minima of H2O. So here is the plot of this concentration of O in each of these species, taken at that radius, I think maybe in the mid-plane. And so what we found is that there is a combination of species that kind of create an invariant with time, that the concentration of this combo does not change with time. So what it says is that any chemistry that happens here happens between them. And what we found. So we'll look at the dotted ones here because the effect is more pronounced here. And so H2O gets photodissociated by Crips into H and OH. On the other hand, we have CO. At this point, it's not cold enough for CO to be fully on the dust, but what can happen is that what is happening is that it's cold enough for CO to get onto the dust and stay there for enough time for something to react with it. And this is it's so-called CO chemical depletion. When you deplete CO by transforming it into something else. And so this is what happens, is that CO gets onto the dust, and here we have OH from H2O, and it reacts with CO and creates CO2. And you can see it here. So you see that H2O is depleting because it's getting photo dissociated, and this OH is then caught by CO, which is getting also depleted, and is transformed into CO2, and as you see that it's rising. On the other hand, CO2, well, it's also getting photo dissociated by Crips into O and CO. So some of the CO2 kind of returns to CO, but this O that is created this way is reacting with O2, which similar to CO finds itself on the dust, and it turns into O3, the ozone, which you can see is increasing whilst O2 is decreasing. And it all happens this way until there is H2O is so depleted that the reaction of turning CO into CO2 is no longer efficient. And you see this break. It kind of happens almost when these two lines cross each other. So you see a break in the pattern, and so H2O is obviously still depleted through reactions with Cripps, but whatever it produces is no longer enough to sustain this chemical depletion. So CO stops from decreasing, and CO2 stops from increasing. And there is also, and after this turn, it even starts to, CO2 starts to decrease while CO starts to increase. And this is because of this photodissociation that I've told before, that CO2 is getting dissociated into O and CO. So CO returns back from CO2. And that O still goes into O3. But we see here that O2 starts to return back. And this is because O3 starts being efficiently dissociated by Cripps. So it kind of returns O2 back. It's kind of, there is kind of a flux of O from this, and this kind of creates O2 and O3, and O3 is returned back to O2 and O. So it's kind of like would, in idea, reach some equilibrium at some point, I suppose. So this is what happens. And the dotted lines, and this is like, we are sure that this is the effect of Cripps, because this is the only difference between blue and dotted line, solid and dotted lines. This is for sure. We also see this effect of chemical depletion in the second model as well, and the depletion of H2O. But I have to admit that that we did not look, I don't remember, but I think we did not look that far into what happens in the second model. We focused on the third model. And I cannot guarantee that in the second model, creep reactions are the drivers of this evolution just the same way that they are here in the dotted case. Because in the dotted case, they obviously are, because this is the change due to increase of the reaction rates. Here, in this default case, I cannot guarantee that. I don't remember, and we have not written about it in the paper. So, like, the chemical depletion of CO obviously goes on here, right? And probably H2O is also a part of it, because again, this line is kept constant. And I guess O2 and O3 are also kind of here to some extent, because they were. I mean, although O3 is kind of 0, so, but kind of O2 was definitely maybe reprocessed into something here, because it kind of decreased into nothing with O3, because like there is a more complex behavior with this O2, O3. I'm a bit more unsure about how the process goes on here. Are creeps the dominant factor in this? Like, are they still dominant in just the time scales are different because the rates are less, or some other processes are now dominant and lead this chemical depletion. I don't know. But creeps, when adjusted, when rates are adjusted, are definitely dominating this process. They're definitely defining this process and lead to an obviously noticeable effect in ice mass fraction. So this is the conclusions. Very simple, that if we take ionization fraction, they don't matter, but for ice mass fraction and maybe more importantly for the CO chemical depletion around CO2 snow line, they're important as well. And having that, now that I'm like working on a paper where we investigate how CO flux is influenced by model parameters and how including CO chemical depletion is actually very important to this flux and how you estimate parameters from the flux. Now I see that due to this impact on CO depletion, it may be important to that as well. So the overarching conclusion is fix your CRIP reactions rates, babes. It can actually be, it does have an impact on the main species in terms of mass. Yeah. That's it. Thank you for listening, and I hope you liked it. Stay tuned for paper and archive maybe.